Rahim. Assalamu alaikum, dear students. I am Sahib Noor, and welcome to another lecture of Electromagnetic Field Theory. This is our lecture number 9, and we will study numerical problems of chapter number 2. The title name of the chapter is Vector Analysis, and the numericals are related with to develop vectors, unit vectors, and the magnitude of vector from given points, and then we will study the products of a vector and will also obtain the angle between any two vectors. And in final part of this lecture we will discuss some conversion in which the expression will be given in the Cartesian coordinate and we will convert them in the spherical coordinates. So let's start our first numerical problem, in which we have to write the position vector in Cartesian coordinate. We will also find its magnitude and direction. The point of the position vector is given as 2 minus 2 minus 1, which means that we have to draw the x-axis, the x component of this position vector, which has magnitude equal to 2. The y component is also equal to minus 2, and the magnitude of the z component is equal to 1, but we will take it on the negative axis. So in order to draw a position vector, we need a reference point. So in this case, we will take origin as a reference point, and at the origin, all the components, that is x, y, z, equals to 0. So our g vector from the position vector will be equal to 2 minus 0 into ax minus, this is plus sign, but when we subtract the y component of at the origin from the y component of the g point, so we will get minus 2ay, and then we will subtract the z component at the origin from the z component of the g, so we will get minus 1. So our position vector will be 2ax minus 2ay minus az, and we can find the magnitude of vector g by taking the square of the coefficient of ax, ay, and az, which are 2 square plus minus 2 square plus minus 1 whole square, and we will take square root, and our answer will be equal to 3. And finally, we can find the direction of a vector g, or unit vector along g vector. So our formula will be g vector divided by its magnitude, as we have obtained the vector g in the first part, and the second part we have also obtained the magnitude of the vector g, which is 3. So we can write vector divided by its magnitude 2 divided by 3 ax minus 2 divided by 3 ay minus 1 divided by 3 az. So we divide each component of vector g by its magnitude, and thus our unit vector will be equal to 0.667 ax minus 0.667 ay minus 0.33 az. So we have three components of a unit vector along g. In second problem, we have to obtain a vector, unit vector, and the magnitude of an expression at some given point. So in this problem, we will have an expression, and we will put the value of x, y, and z, and will get the vector form of a given expression. And then we will have to find the unit vector and the magnitude of the given vector. So our vector is s, and the expression of s is given by this, in which s is a function of position. So here in x we have to put the value of x, which is 2, the value of y, which is 4, and the value of z, which is 3. So we will find the expression, the vector form of s on these given points. So after putting the value of x, y, z, we will have 3 components of vector s, which is 5.95 ax plus 11.9 ay plus 23.8 az. And in the second part, they ask that we have to determine a unit vector which gives the direction of s at p. So at the given points, which are 2, 4 and 3, we have to find a unit vector. And for a unit vector, we know that the unit vector can be obtained when a vector is divided by its magnitude. So first we will find the magnitude of s from this expression, and we will write sx square plus sy square plus sz square under the root, and then we will divide each component of s by the magnitude of s. So we will divide these 3 components on the magnitude of s, and we will obtain 0.218 ax plus 0.436 ay plus 0.873 az. So this is a unit vector of s at p, and again the unit vector has 3 components. But remember that when a unit vector has 3 components, then the coefficient of ax, ay and az must be less than 1. At the third part of this question, they say that find an expression which is a function of x, y, z, on which the magnitude of the s is equal to 1. So we will take magnitude of s is equal to 1, and we will have to obtain an expression which is function of x, y, z. So the formula for the magnitude is simple, as we have to take square of the coefficient of base unit vector, and after some algebraic calculation we will find that the expression which is function of x, y, z is equal to x minus 1 whole square plus y minus 2 whole square plus z plus 1 whole square under the root, and this will equal to 125. In this problem, 3 vectors are given, which is given as a have 3 components, b have 2 components, and c have 2 components as well. And we have to do multitask. First, we have to obtain unit vector of vector a, and the unit vector formula is vector divided by its magnitude. This is vector a, vector form of a, and we will divide the vector by its magnitude, and we will obtain the unit vector. In second part, we have first develop a minus b, that is, the element of b should be subtracted from the element of vector a, and we have a vector, and then we will find the magnitude of this vector. So this is a minus b, this is a minus b, and to find the magnitude we will take square of the coefficient of this vector. So the coefficient are 1, so 1 square plus 6 square minus 4 whole square, and we will get under the root 53. In third part, we have to find the dot product of a and b. So we will first write the component of vector a, then we'll put a dot, and then we'll write the component of vector b, and we'll multiply their components such that our formula will be a dot b is equal to ax bx plus ay by plus az bz, and our answer will be equal to minus 11. And in the fourth part of this question, we have to find the angle between a and b. So remember that whenever you have to find the angle between 2 vectors, simple use a dot product, and the formula for dot product a dot b is equal to ab cos theta, and for angle we can make the expression is theta ab is equal to cos inverse into A dot B divided by A magnitude, B magnitude. So A dot B is equal to 11. This represents magnitude of vector A, which is under root 14, and this represents magnitude of vector B, which is under root 17. So by calculating this on calculator, we will obtain 135.5 degrees. And in the fifth part of this question, they asked to find a component of vector A in the direction of C. So we have to calculate the component of vector A in the C, along the C direction. So in this case, we need the unit vector of vector C, AC, which represents the unit vector of C, and will multiply it with A in dot operation. So first we have to obtain a unit vector of C. So we will divide C divided by its magnitude. So vector C is given as 5ax minus 2az, and the magnitude of this is under root 29. And then we will multiply the x component of C with the x component of A, the z component of C with the z component of A, and our answer will be equal to 11 divided by under root 29. The remaining part of this question are to obtain the cross product of vector A and C. And remember that for cross product we will use the determinant formula, and we have to take a 3 cross 3 matrices. In first row we have to write the component of base unit vector, which are ax, ay, and az. In the second row we have to write the element of vector A, and in the third row we have to write the element of vector C. And then we will expand the determinant by row first, and our answer will be equal to minus 4ax minus 13ay minus 10az. So this is the cross product of two vectors, or vector product of A and C. In the seventh part of this question, we have to obtain the scalar triple product. We have to multiply A with B and C such that the answer is a scalar quantity. So A dot B cross C or A cross B dot C, these are the similar expressions. So A dot B cross C is equal to C dot A cross B. You can write C first and then dot, and will write A cross B at the last. So the answer will be the same. And whenever we have a scalar triple product, we will use the determinant method, in which, as we have three vectors, so in first row we have to write the element of vector A, in second row we will write the element of vector B, and in third row we will write the element of vector C. And you can also write a 3 cross 3 matrix in which the first component, first row will represent the element of vector A, the second row will represent the element of vector B, and the third row we have to write the element of vector C, and our answer will be minus 42. The last part of this question, in which we have to obtain A cross B cross C, and then A cross bracket B cross C bracket close. So remember that we have studied in the lectures that we have to apply Bake minus Cabe rule on this like multiplication, in which the last two vectors are closed in the bracket. So we will apply Bake minus Cabe rule on this. So this is A, whenever we have to multiply A cross bracket B cross C, we will apply Bake, this is Bake minus Cabe rule. Remember that this rule is applied whenever the last two vectors are closed in bracket. In this form, the first two vectors are closed in brackets or appear in brackets, so we can convert this expression in
this like expression. So first we have to change the order. If we change the order, so we have write C vector first, C cross A cross B, then we will have a negative sign, because whenever in cross product you are changing the order of vector, so you must put a negative sign. And in second step we will also change the order of the brackets vector. So we will write B cross A and we will have a negative sign as well. So we have two negative signs and they will multiply and our expression become positive, and then we can easily apply Bake minus Cave rule on this expression as well. So your final expression for A cross B into C is equal to 2ax minus 40ay plus 5az, and similarly A cross B cross C, and you will get 55ax minus 44ay minus 11az. Now in this numerical problem we have to find a unit normal vector. A unit normal vector means a vector which is perpendicular to a plane is known as a unit normal vector. And we have a plane which intersects x-axis at point 1, 0, 0, y-axis at 0 to 0, and z-axis at 0, 0, 3. So now for a plane we need two vectors. To construct a plane we need at least two vectors. So let this represent our vector A and this represent our vector B. So in first problem we obtain that whenever the points are given we can easily construct the vector form from these points. So let this represent our vector A, and let this part is represent a tail part of vector A, and this represent a head part of vector A. So we will subtract these points from these points. So 0 minus 1, and we will put a base unit vector which is ax. So minus 1 ax, 2 minus 0 into ay. So our y component will equal to 2 and the z component is 0. So let vector A has two components because the z component is 0. And similarly let this represent vector B, and let this represent the tail of vector B, and this part represent the head of vector B. So we will subtract these points from these points, and this we will have a vector B, and we will use the cross product and we will have the resultant of these two vectors. So let A and B are the two vectors and C is their resultant. So we have construct A and B, and to obtain the resultant vector we will use the determinant form. First row is for the base unit vectors which are I, J, K. Up to here we use notation AX, AY and AZ. In second row for the element of vector A, and the third row for the element of vector B. When you expand this determinant you will obtain the resultant vector is 6i plus 3j plus 2k. And in order to obtain the magnitude of vector C, we will take square of 6, 3 and 2. So 6 square plus 3 square plus 2 square, which is equal to 49, and the square root of 49 is 7. So finally we will obtain the unit vector which is parallel to vector C. So this is also called the normal unit vector of this plane which is perpendicular to this plane. So as C is perpendicular to this plane, and we can write the normal unit vector whenever vector divided by its magnitude, it will give us a unit vector. So n cap represents the unit normal vector, and we will divide the component of vector C which are 6. So 6 divided by 7i plus 3 divided by 7j plus 2 divided by 7k, and this is our normal unit vector, and you can easily check it by obtaining the magnitude of this unit vector. We will get 1.
So before solving the next problem, we have to write the unit vectors of spherical coordinates and their expression. So we have 3 unit vectors in the spherical coordinates, which are r cap, phi cap, and theta cap. These are the 3 unit vectors. And remember that a unit vector can be written as vector divided by its magnitude. And the vector form of the position vector is equal to x into x cap plus y into y cap plus z into z cap divided by its magnitude. So the upper part represents the vector form and the lower part represents the magnitude. Remember that we have studied in our lecture the unit vector is x ax plus y ay plus z az. So x cap, y cap and z cap are similar as ax, ay and az. And in lecture we have studied that the x in the spherical coordinate can be written as r sin theta cos phi. So here we have to write r sin theta cos phi. For y we have to write r sin theta sin phi, and for z we have to write r cos theta. So in each term there is r. So in x we have r, in y we have r, and in z we have r. So we will take common the r term, and r will cancel with the lower r. So we will have remaining with sin theta cos phi x cap or ax plus sin theta sin phi y cap or ay and cos theta z cap or az. So this is the unit vector of the spherical coordinate in the radial direction. And then for obtaining the phi cap or phi unit vector, we have to remember the expression or we have to remember the definition. So z cap cross r cap, this is the cross multiplication, and we will divide this expression by sin theta. So r cap, this is the value of r cap, and we will multiply the we will take the cross product of each component of r cap with a z cap, and we will obtain minus x cap, and you can call it ax sin phi plus y cos phi. And for theta cap, you have to remember this definition: phi cross r, or the cross product of phi cross r. R, we have studied that a theta is equal to a phi cross a r. So now you will have to take the cross product of phi cap with a r cap. You can use the determinant form or manually, and you will have 3 components of theta cap as well. And this is x component, y component, and the z component. Remember that these are unit vectors, and if you confirm that these are unit vectors, you have to take its magnitude. If their magnitude become 1, so you will call it a unit vector easily. And then we have to take the dot product of unit vector in of the spherical and the Cartesian coordinates. So if we are going to take ax dot ar, remember that this is our ar. So when we take the dot product, only the x component will multiply. So this is the x component in the Cartesian coordinate, and this is the x component of ar in the spherical coordinate. So this multiply with the ax, and ax dot ax is equal to 1, and we will remaining with the sin theta cos phi. And then if you take the dot product of ax with a theta, so here ax dot a theta, this is a theta. So again
the x component will multiply, and you will be remaining with the cos theta cos phi. This is cos theta cos phi. And then if you have to take the dot product of ax with a phi, so here the x component is minus sin phi. So we will have only minus sin phi. And similarly, you can take the dot product of ay and az with the ar, a theta, and a phi respectively. So now let's move to our problem. In this lecture, in this problem, we have to convert the expression of g which is given in the Cartesian coordinate, and we have to transform it into the spherical coordinate. So in order to transform the expression of z from Cartesian to spherical, we have to take the dot product of g with ar, a theta, and a phi. So when you take the dot product of g with a r, so this will be our gr component, and the value of g is given as x z divided by y ax, and we have to multiply it with the ar. Now using the table to obtain the value of ax dot ar, which is sin theta cos phi, and now we have to convert x, y, z into the spherical coordinate. For x we have to write r sin theta cos phi. For y we have to write r sin theta sin phi, and for z we have to write r cos theta. Now we will have gr, the value of gr, r sin theta cos square phi divided by sin phi, because in y we have sin phi term as well, and sin theta will cancel with the sin theta. And similarly we have to obtain g theta and g phi, and then finally we will write the expression of g a, and this is the common term. This will come in the all three components of g. So r cos theta cos phi is the common term, and in the bracket we have sin theta cot phi means cos phi divided by sin phi into ar plus cos theta cot phi a theta minus a phi, and this is the vector form of g in the spherical coordinate. So this is our lecture number 9, and I hope that you will understand this lecture. And in this lecture we have solved some problem in which we write the vector form of a given point, and we have also multiplied vectors, the dot product of vectors or the cross product of vectors. Even we have studied the scalar and vector triple products, and finally we convert the Cartesian coordinates of a vector into spherical coordinates. And in next lecture we will discuss the gradient, divergence, and curl along with the integral calculus. I hope that you will understand this lecture, and if you have any question you can ask me at my email. Till then, Allah Hafiz.